Hey, this is Mr. Ayton. Welcome back to Pre-AP Chemistry. We are in a new unit, Unit 11, Acids and Bases. We are in week 23. What are we going to look at in week 23? We're going to look at Arrhenius acids and bases and Bronsted-Lowry acids and bases, the two models of acids and bases. And Arrhenius was a model that was developed to really deal with strong acids like hydrochloric acid, hydrobromic acid, hydroiodic acid. You can see HF is not in that list. Nitric acid, HNO3, and sulfuric acid, H2SO4, and the last one is perchloric acid, HClO4. And what do we know about these strong acids is they dissociate 100%. They ionize 100%, which means if you have HCl, and that HCl is going to break up into H plus and Cl minus, H plus and Cl minus, H plus and Cl minus. You can see this HCl is broken up, ionizes 100%, which means it is also a strong electrolyte. It's going to conduct electricity very well. Why? Because there are free ions, free positives and negatives that are rolling around in the solution. You can see the pH values are going to be very low, maybe around pH of about 1 or pH of about 1 or 2, something like that. Why is it going to be such low pHs? Because there's such a high concentration of H plus in the solution, which means we're going to be able to use our pH equations immediately. Well, guess what? If we have strong acids, Arrhenius acids, we also have strong bases, which are Arrhenius bases. And these also dissociate 100%, which means we don't have lithium hydroxide, sodium hydroxide, or potassium hydroxide. We have Na positive, if we have sodium hydroxide, OH minus. You can see Na plus and OH minus. As you can see, the OH minus is very high in concentration. It's also going to be strong electrolytes because we have free positives and negatives that are in the solution, which means it's going to conduct electricity very, very well. You can see the H plus, there's no H pluses in there. There's a high concentration of OH minus, which means your pHs are going to be very high, like 13 or 12, something like that. So the pH values are going to be very, very, very high. You're also going to be able to use your pH equations immediately as well using Arrhenius, strong acids and bases. Well, after the Arrhenius model, we also have what's called the Bronsted-Lowry model. The Bronsted-Lowry model is, of course, dealing with weak acids and weak bases. And this Bronsted-Lowry model is really has a different definition of what an acid is. You can see the Arrhenius model said an acid was something that dissociates 100% into H+. Well, guess what? The Bronsted-Lowry model says that the acids are proton donors, H plus donors, which means you can see this HC2H3O2 is a weak acid. It's going to donate an H+. What is the H2O going to become when it becomes H+? It's going to become H3O+, aqueous. And what's going to get left when this HC2H3O2 loses an H and loses a plus is C2H3O2 minus, aqueous, which you can see this H3O plus tells you exactly how much H plus or H3O plus, same thing, is in the solution, which means you can see how this is not going to dissociate 100%. This is not going to break up. This HC2H3O2 is not going to break up into H plus and C2H3O2 100%. It's only going to dissociate a very small percentage. So if you had 100 particles of this, only 5 particles and 5 particles, approximately, would be split up, ionized into H2O plus and C2H2O2 minus, which means if you don't have a lot of H plus, your pH is going to be still below 7, but maybe a pH of about 5 or a pH of about 6, something like that, not a pH down near 1, which also means it's a weak electrolyte. You can see HC2H3O2 is not going to break up. It's going to be one molecule, HC2H3O2. I would have to have 100 of these, and I would only have 5 of them split up in the H plus and C2H3O2 minus. I would have to have 100 of these HC2H3O2 molecules in order to have 5, or well, really 95 and 5, in order to break up into these particles. Okay. Well, here's another example. HF. HF is a weak acid, which means HF is going to donate an H plus. And what is the H2O going to become? Is H3O plus, aqueous. And what is the HF going to become when it loses an H and loses a plus? It's going to be F minus. Hopefully not your grade. Okay, is F minus. Now, if you can see, on this side of the equation, we knew HF was a weak acid, which means water acted like a weak base. Water accepts the H plus. The HF donates the H plus. And on this side of the equation, you can see how we call this thing with all the H plus a conjugate acid. That would be the H2O plus. The other substance is a conjugate base. So the F minus or the C2H2O2 minus would be what's called your conjugate bases. Well, we also have Bronsted-Lowry bases, and where we said Bronsted-Lowry acids were H plus donors, then a Bronsted-Lowry base would be an H plus acceptor. An H plus acceptor. You can see NH3 we know is a weak base, which means the water is going to act like an acid and give away an H plus. So what will the NH3 become when it gains the H plus? It would be NH4 plus aqueous, okay? NH4 plus. What will the H2O become when it loses an H and loses a plus? It would be OH minus aqueous. And you can see that's what tells you that this is a weak base, is that it produces OH minus. A very, very, very small percentage of OH minus, but it's still going to produce a little bit of OH minus. And it's only going to dissociate less than 5%, which means if you had 100 particles of this, only 5 particles and 5 particles would break up into the NH4 plus and the OH minus, which means you're going to have a bunch of NH3 in the solution. It's not going to dissociate. It's not going to ionize. It's not going to break up very much. Only a small percentage is going to break up in OH minus and NH4 plus, but a very, very small percentage, which means, again, the Bronsted-Lowry acids and bases are weak electrolytes. They don't conduct electricity. The pH is going to be maybe a pH of about 9 or something like that. It's going to be above 7, but it's not going to be a very, very, very low or high pH at all. And what do we know on this side of the equation? The conjugate acid has all the H plus. You can see this NH4 plus has all the H plus. The thing that does not have the H plus would be what's called your conjugate base. So the OH minus would be your conjugate base. And that is a great introduction to Arrhenius acids and bases and Bronsted-Lowry acids and bases, our 2 models of acids and bases. And that's Unit 11, Acids and Bases, Week 23. I'll catch you on the flippity flop. See you guys. Bye.